Hello everyone, and thank you for choosing this special session. Today I would like to discuss with you Markov-transformable processes, how to formulate the governing differential equation and how to numerically solve them. My name is Leandro Iannacone and I have conducted this work at the University of Illinois Urbana-Champaign together with Dr. Armin Tabande and under the supervision of Professor Paolo Gardoni. Time-varying problems are ubiquitous in science and engineering. Think, for example, of the life cycle analysis of engineering systems or classical random vibration analysis. But we could even find this type of problems outside of engineering, for example, when we look at the spread of contagious diseases or at the stock market prices. To describe these time-varying problems, we typically use partial differential equations, PDEs, or stochastic differential equations, SDEs. PDEs provide a mathematical description of these phenomena, but they typically do it in a deterministic way. SDEs, on the other hand, extend the theories of PDE to look at the evolution of the distribution of the variables of interest, hence accounting for the uncertainty in the processes. So solving PDEs and SDEs has always been a long-standing challenge because of the complex phenomena that are described by these differential equations, because of the complex geometry, large-scale physical domain, and high-dimensional inputs, and of course because of the presence of the different sources of uncertainty. Simplifying assumptions are typically made on the equations that describe this phenomena. Most commonly, these processes are assumed to be linear or to satisfy the Markov memoryless property, by which we mean that the evolution of the system at any given time only depends on the current condition regardless of the entire history of the process up to that point. And this type of assumption comes with several advantages, including the use of the Fokker-Planck equation to obtain the distribution of the variables of interest. And we would go into more detail about the Fokker-Planck equation in a second. However, some phenomena can exhibit non-Markov behaviors. These problems need to be cast into an equivalent Markov formulation if we want to use the advantages of such formulation. And we can use for this casting some available procedures such as the stochastic averaging detailed in Lin and Kai 1995. And a comprehensive framework that details how to cast the non-Markovian problems into a Markov formulation and how to efficiently obtain the distribution of the variables of interest is currently not available in the literature. So in this work, we present a three-step procedure to model the evolution of time-varying systems. In this procedure, first we formulate a general Markov formulation that describes the evolution of the system. Then we detail how to cast problems that exhibit non-Markov behaviors into such Markov formulation. And then finally, we propose an efficient method to solve the Markov formulation. This is the outline of the presentation, and I would like to start by discussing the formulation of the general Markovian equations. So in a general Markov formulation, the evolution of the state variables of a system can be described using stochastic differential equations. This that I'm showing here is how a typical SDEs look like. We are modeling the infinitesimal change in the state variable x, so dx, and this is given by the sum of two components. The first component quantifies the deterministic change with time, and it's the product of a drift coefficient mu and the infinitesimal time dt, whereas the second component quantifies the evolution of the uncertainty over time, and it's the product of a diffusion coefficient sigma and a driving noise ds, which determines the shape of the process. So if we use this type of equation, we can look at this problem as a random vibration problem with a known model form. And this formulation has been used in the literature in engineering for different cases. For example, Iannacone and Gardoni used it to model the evolution of engineering systems subject to deterioration. Such formulation assumes the Markov memoryless property, and in particular, if we assume that the driving noise is a Brownian motion, we can solve this problem using the Fokker-Planck equation. The Fokker-Planck equation is a partial differential equation where the quantity of interest is the probability density function, or PDF, of the variables of interest, of the state variables. And because we are now using a deterministic partial differential equation rather than a stochastic differential equation, solving this problem has become significantly easier. We now want to extend this formulation to problems that exhibit non-Markov behaviors. Here I'm showing the equation that we use to describe this kind of problems. We are still modeling the change over time of the state variable x, but here we have some deterministic nonlinear functions, but most importantly, the driving noise are random excitations with zero mean and a certain cross-correlation function, which makes the process non-Markov. So in order to cast this into a Markovian formulation, we need to find the equivalent drift and diffusion term. And because we can transform these processes into a Markovian formulation, we call them Markov-transformable. In order to do so, we first recall the mathematical definition of the drift and diffusion components, which can be written as a function of the expected value of the finite increment of the stochastic process over a certain time interval dt. And then we write this finite increment for the general non-Markovian formulation. We take the first order approximation of the nonlinear functions. And then combining all the equations, we obtain the equivalent drift and diffusion term. So now that we have an equivalent drift and diffusion term, we can describe the problem with an equivalent Markov problem, which means that we can solve it using the Fokker-Planck equation. While solving the Fokker-Planck equation is significantly easier than solving the original stochastic differential equation, it can be still complicated because we are talking about a partial differential equation in multiple dimensions. So we also propose a novel method to solve the Fokker-Planck equation. Our idea is similar to the ones proposed in previous works, such as the equivalent linearization method, the tail equivalent linearization method, and the Dirichlet process mixture. However, the formulations available in the literature operate on realizations of the system response. In other words, the response of the system is first typically simulated with Monte Carlo, then approximate distributions are fitted to the simulated closed-form response. Our method instead works directly on the equation defining the problem, and as a consequence, we do not have to generate simulations of the process first. We are also able to look at the transient solution of the problem, not just the steady-state response. So we want to find the solution that best satisfies the Fokker-Planck equation. To do so, we construct the approximation function space by a mixture of Gaussian distributions. This construction replaces the original nonlinear system with an unknown number of linear systems. Then we substitute the trial function belonging to this approximate solution space into the Fokker-Planck equation, and using the linearity of the differential operator, we obtain the residuals of the Fokker-Planck equation. We then minimize these residuals over the entire domain to obtain the best possible solution. When solving these minimization problems via complicated integrals is unfeasible, then we can evaluate the residuals at a selected number of points and minimize the value at those points. We can evaluate the value at a grid, and the points of the grid can be weighed equally or can also be weighed based on their importance, as proposed in Tabande et al. 2022. I want to showcase the performance of the proposed framework by looking at an example. This is the stochastic differential equation that we're looking at. These are the unknown parameters, and the equation is driven by a stationary process which has zero mean and a certain autocorrelation function, which is what makes this equation non-Markov. So first we need to find the equivalent drift and diffusion term for the equivalent Markov process using stochastic averaging. This is done with these equations shown here, and at the bottom I'm showing to the left 1,000 realizations of the original process and to the right 1,000 realizations of the equivalent Markov process. You can see how, at least qualitatively, the processes behave in the same way. For a more quantitative comparison, we can find a closed-form solution of the equivalent Markov process, which in this case turns out to be an Ornstein-Uhlenbeck process with time-varying drift coefficient. For this type of process, we have a closed-form solution for both the first and the second moment. And here at the bottom, I'm showing a comparison between the first and second moment of the original stochastic differential equation and the equivalent Markov formulation. And you see how, even quantitatively, we have a satisfactory comparison between the two. So now that we have an equivalent Markov process, we can now find an approximate solution to the associated Fokker-Planck equation. For this problem, we assume the approximate solution to be normal with time-varying mean and variance, and both mean and variance are fifth-degree polynomials of time with unknown parameters. So this means that we have a total of 10 parameters to calibrate. And to facilitate the search of a minimum, we focus on the first 5 seconds of the process. We perform minimization, and the minimization reaches convergence. So now we can compare the mean and the standard deviation with the exact value that comes from the closed form solution. You can see from these figures how there is some discrepancy, but this is due to the limiting nature of the approximation PDF, which we selected as a single normal distribution with time-varying polynomial mean and variance. So if we selected a mixture of multiple distribution, and also if we allowed different calibrations at different time instants for the unknown parameters, then the results are expected to improve, which is what is done in Tabande et al., which I invite you to check out. So concluding, we propose a mathematical framework to model the evolution of systems over time. The proposed framework models the evolution of the state variables using a system of stochastic differential equations that satisfy the Markov property. We extend the formulation to systems that exhibit non-Markov behaviors by detailing a procedure to cast the non-Markov processes into a Markovian form, so that the Markovian form allows us to work with the Fokker-Planck equation, which is a deterministic partial differential equation. We also propose a formulation to solve the Fokker-Planck equation, and the proposed formulation works directly with the partial differential equation and does not require simulation or closed form realizations of the process. The proposed formulation can be used to model time-varying problems, such as deterioration of engineering systems, where the state variables are the physical properties of the system that evolve due to adverse environmental conditions and shocks. So this concludes my presentation. I welcome any questions.